Look at this clip of the man running. All of a sudden, and we're back. What could have happened in that interval? We don't know. We can't define what happened there. The man may have been replaced by his look-alike. He may have thrown something. Or he could have just continued running. But all this is just speculation. What happened there is unknown. Limits are not very different. It is the value of a function at any point. Ideally, a discontinuity in a graph should be represented by a white dot, but I left some gap for our understanding. I have this function f of x which equals x plus 2. But I have also placed a condition. X can't take the value 1. So at the point where x equal to 1, f of x is not defined in this case. But by looking at this graph, the value seems as if it must be 3. If we join these 2 points, then the value 1 looks like it should be 3. So the limiting value of f of x at 1 is 3. Limits are not necessarily defined only on discontinuities. For example, if we take the limit as x tends to 2 of f of x, then it's still very much 4, despite no discontinuity being at that particular point. Now let's define limits more formally. Let f of x be a function that's defined around the point a. L is the limit represented by this, and it's read as limit as x tends to a f of x. It exists only if for a positive number epsilon there is a positive delta such that 0 less than modulus of x minus a less than delta, then modulus of f of x minus L less than epsilon. Let's take another example. I have this limit as x tends to 0 of sin x by x. If I plug in the value of 0 into this function, I get 0 by 0. This is called an indeterminate form. There are 7 indeterminate forms: 0 by 0, infinite by infinite, 0 into infinite, 1 power infinite, infinite minus infinite, 0 power 0, and infinite power 0. In that case, we must manipulate the function by rationalization, algebraic elimination, or by using L'Hopital's rule, which I won't be covering over here. If I plug in 1, I get this value. As I start plugging in values that are smaller and smaller, we tend towards 0, not 0, we tend towards 0 and get as close to 0 without actually being 0. As we do this, the values of the function also start tending towards 1. From this, we can conclude that this particular limit as x tends to 0 of sin of x by x equals 1. There are proper proofs for this expression which can be found. Next, for the existence of limits. A limit exists only when values of the limit are equal whichever side we approach it from. The left-hand limit of a function must equal the right-hand limit. For this function, modulus of x by x, limit x tends to 0 does not exist, as the value of the limit is minus 1 when approached from the left side and plus 1 when approached from the right. Limit of x tends to 0 of x square exists as its value is 0 regardless of whether I approach it from the left or from the right. If I define two functions f of x and g of x such that limit of f of x as x tends to a equals k and limit of g of x as x tends to a equals L, then they satisfy all of these four following properties. This one is where I multiply alpha, a constant. Over here, I add these two functions f of x and g of x, or I subtract these two functions f of x and g of x. Over here, I multiply these two functions, and over here, I divide these two functions. Next, I have the Sandwich Theorem, aptly named so. If a function is sandwiched between two other functions, its limiting value is that regardless of whether the other functions are defined there or not. This is the statement of the theorem. If g of x less than or equal to f of x, which in turn is less than or equal to h of x, for any x in an interval around a, and limit as x tends to a h of x equals limit as x tends to a g of x equals L, then limit as x tends to a f of x is equal to L. This is the statement of the theorem, and this one is a pictorial representation.